to this first distinguished lecture sponsored by ISTEC. ISTEC, which stands for the Information Science and Technology Center here at CSU, is a university-wide organization that covers all aspects of the information sciences and technologies, including research activities, education, and outreach. One of the activities that we do hold is the Distinguished Lecture Series, of which today is the first. I'd like to get the host of today's speaker up here, Emma Ebert Lopov.
Thank you. I'm delighted to be able to introduce Vipin Kumar. He is a Regents Professor at the University of Minnesota in the Department of Computer Science and Engineering, and he also holds the William Norris Endowed Chair. And I'm not going to go through all the stuff that you can find in his bio because you saw the announcement. I want to tell you a few other things. So first of all, early on, he worked in parallel computing, and HJ can tell you much more about that because the two of them know each other from them. And then later he focused more on machine learning and especially discovery from data. And he used those in many different disciplines, so in the health sciences, bioapplications, and earth sciences. He has graduated 40 PhD students, and about 1/3 of them are now in faculty positions. And just to give you an idea of how much impact he's had, so many of his students worked, say, in health policy applications, data-driven health policy and the like. So 5 of his faculty members are actually in medical schools and transfer this data-driven approaches now to medical sciences. And then it's not unusual when his group develops tools that really impacts lots of other domains, for example, in the earth sciences. So, for example, I just recently heard that one of the tools they built, there was basically a workshop afterwards for ecologists just to brainstorm, okay, we have this great new tools that come from there. We can do now all these things. How does it change research in ecology? So he's impacted entire fields. And just to give you some of the examples, I mean, he's going to talk about many of them, but a lot of them have to do with interpretation, for example, of satellite images. So you start with satellite images and you start with the raw data, but then you throw in some either physics or constraints or other things to make things more robust. And so detection of ocean eddies from satellite images, detection of water on Earth, water maps that are being used by ecologists, detecting land cover changes, especially due to wildfire. So those are many things. And again, his tools really goes on in the other areas and impact those areas as well. Personally, I've known him mainly because I'm trying to coordinate this whole climate informatics community. And Vipin has probably been the most important person. When we have our workshops, 1/3 of the students presenting are his anyway. And he's, for me, I think I never told you that, but you've been a great role model. And whenever we had our doubts, we were thinking, well, can machine learning really do something for the earth sciences? We just had to look at his research. It's like, hey, Vipin students, they have so many success stories that kind of made us more optimistic. And it's like, yeah, there's a lot that can be done because we see the success stories. And I've always asked him, or often asked him for feedback over the time. He's great to collaborate with. He's fun to work with. He smiles a lot. And he's also, and I think that's very rare in people, in very well-known people like him, he's an extremely good listener. So he will really listen to what even grad students have to say. If somebody just lifts a finger, he will be quiet and really listen. And I really appreciate that. So without going into more detail, I'm very excited to let you see what exciting work he's doing.
Thank you, Ime. And it's a really pleasure to be here. And of course, I listen to the students because I learn from them all the time. So I don't let any of them graduate until they teach me enough. So this talk is about, is it too loud? Maybe I'll just put it a little bit lower here. So this talk is about this idea that machine learning, a field that's revolutionizing everything we do in our life, what could it do for some of the most pressing problems that are facing the humanity, in the area of climate and environment. And of course, machine learning requires lots of data, but we have lots of data in the climate and environmental sciences. And it's coming in from many of the same developments in technology that have sort of fueled all of these different sectors that have sort of, which machine learning is prominent in, which is being able to design instruments and sensors that can collect a lot of data. And in environmental sciences, that started happening about 40 years ago with satellites. And the other big driver of data in scientific domains has been the computers. The computer models generate a lot of data. And then you're seeing here the Earth system model from a place not too far from here, the NCAR. So, and then these models are getting more and more sophisticated over a period of years. If you look at a model like this from 20 years ago, it would look very, it won't be able to resolve a lot of these features. But now, models like these are very, very sophisticated. So between the sensors from the sky, sensors on the Earth, sensors of the environment, models, massive amount of data is being generated to the point that the environmental science community sort of considers this area to be a big data science. Very much similar in its in magnitude and potential as we have seen the transformation in biology and the genomic sciences. If you look at 30 years ago, people were beginning to see that yes, we can do these high throughput experiments using this technology, and the technology developed very, very rapidly over the last 30 years. And of course, nobody in biology would sort of would consider the importance of informatics, would ignore the importance of informatics, and same thing is beginning to happen in sort of climate sciences. But the problem is that the nature of the data is in the climate sciences, in the urban sciences, is so different than what you end up seeing in the commercial world. The kind of data that the Googles and the Facebook have to sort of deal with is very different in nature, and partly because the data that you're sort of that's being collected when you're on a Facebook has a very concrete nature to it. We know exactly who the people are, the nodes, we know who they're connected to. You may be purchasing certain items, so you know exactly which person is purchasing what item. You know their information about individuals in a very discrete level. Whereas in the environmental sciences, you are actually collecting data which is surrogate. This is you're sort of trying to capture a physical process through different means, and the processes are happening at different scales in space and time, and the sensors will only capture certain aspects of them. The phenomena that you're trying to capture is dynamic, is evolving, and it's very hard to sort of convert that data into a form that can be applied to the traditional machine learning algorithms. That's one part. The other part is these physical processes have been analyzed by the physical scientists over hundreds of years. They're building theories and scientific understanding. And the machine learning tends to come in and sort of say, give me the data, I'll find patterns, right? And the question, how do you reconcile? I mean, nobody in their right mind should think that you could make advances in the sciences without building on top of the layers and layers of information that people have sort of collected. So these are all the challenges, and then of course, if you ignore that information, then you are at your own peril in the sense you'll be finding patterns that are not so useful. So in my group, I have been sort of interested in this area for a long time, and more recently, this work has been funded by this expedition and computing project, which actually just ended, but there are a series of such projects that have been funding these works. And the idea in this project is to be able to take this massive amount of data from different sensors and models and analyze them and get to a point where it could sort of be providing some actionable information to the physical scientists. So now this is just a illustration of different projects that came out of this. This was a long project, had 5 different institutions involved. It was anchored at Minnesota. Half of the team was computer scientists, other half is people from physical sciences, and there are many, many different topics sort of being discussed. I just highlighted only about 6 of them here, just to give you a sense of the breadth of what we sort of tried to cover. So there was this project on being able to understand, analyze the data from the satellites about and this is the data, this is the altimetry data. So satellite is sensing from the sky the height of the ocean at different times. And if you create a heat map of this, you can sort of see that played out in front of you. This is the raw data from the satellite after being processed. And you can sort of see that, yes, some patterns are emerging. This is like the red means the high height, blue means the lower light, and you can sort of get a little sense of that, yes, there are some high-level patterns that may be there. Now, one of the things we use this data is to analyze the movement of ocean currents, like the ocean eddies, which transport heat and chemicals across the world and play a lot of role in the ecology of the ocean. And this has been a very difficult, eddies are extremely important, and yet they're very difficult to study, because only way to be certain as to where the eddies is to sort of put a buoy, and then you sort of see if the buoy is being turned around. And by building this machine learning algorithm that could look at this very uncertain data, but about a physical phenomena, where the phenomena you're interested in is this depressions in the ocean height, and that's sort of moving around. So this required building a series of algorithms and machine learning that could work with certain uncertain data, and it resulted in the first open source database of 20 plus years of ocean eddies and ocean impacts, and along with software, so anybody can use it in the future as we go on. So this was sort of published in the Nature's Scientific Data journal. Now, another direction that sort of is also interesting from a different perspective, and this is looking at the climate data and converting into a graph. Okay? And in computer science, we like to work with graphs because we have a lot of algorithms that can work with graphs. All of this social network analysis that you see is sort of all based on graphs. And it turns out that you can take the climate, the physical space of the environment, and you can sort of break into small regions. Each region can become a node, and the pair of nodes can be connected based upon how related or unrelated the information content is. And then you get a graph. And once you have this graph, then you can try to analyze it using many, many different types of algorithms. You can discover teleconnections. You can discover teleconnections that people knew before, and you can find teleconnections that nobody knew before. And that would be sort of the ultimate utility of this. So, and again, this line of research has led to many, many algorithms and publication in Climate Science Journal. These are the patterns and phenomena identified using this algorithm, but then verified by climate scientists so that they could figure out exactly what the underlying connection is. Now, beauty of these algorithms is that these algorithms, even though they're being run or designed for a climate data, they could be applied to any other algorithm. So for example, similar algorithms have been applied almost as it is into the data that sort of analyzes the activity in your brain. So it's like the brain fMRI data is also a space-time data set, and it turns out you can literally take the same algorithms and almost with very little modification, make them work to find teleconnections in the brain and sort of give you the information about how different components of the brain sort of work together. And sort of the list go on. There are other people in the project who are sort of building a sparse predictive modeling framework. Imran actually has worked with IME on several projects himself as well, analyzing things like uncertainty, which are very difficult to analyze using, which are difficult to capture in the climate models. And there is a whole series of projects that I'm going to spend a lot of time talking about, is being able to understand the phenomena of the anomaly change from the satellite data on the phenomena on the land surface. All of these projects that I'm talking about so far are focusing on either the data from the sensors about the environment, which is sort of looking at the data and then trying to find some patterns that are related from a physical perspective, or they're looking at the data generated by the models and analyzing them, which is over here. But then from from these different projects, a sort of a new direction emerged, which sort of almost started taking shape towards the end of it, but it's sort of taking up a big space of its own, and which is how do you bring in this machine learning aspects and the physical models, and can you put them together into a modeling framework which is much more powerful than either one of them. And even though in the rest of these projects we had to sort of develop algorithms and machine learning approaches that were cognizant of the scientific knowledge, but they really come together in this framework of bringing physics and data together. This is I'm going to give a much more detailed talk on this one is it at 2 p.m. this afternoon, in the context of modeling temperature in a lake, a problem that is typically solved using physical models, but then models in any of the scientific applications tend to be not perfect, because if they were perfect, you would have perfect results, but they happen to be imperfect realization of the reality because they have to approximate things, or there may be some information that's just not visible to us. And as a result, these models have to be parameterized. And when you parameterize them, then they can, if the parameterizations are wrong, they can lead to wrong results. But these parameterizations are often then tuned using observation data. But observation data tend to be not enough to be able to come up with satisfactory parameterization in most cases. So the alternate approach becomes one of looking at this observation data that you're using for parameterization and seeing if it could be used to build empirical models that could sort of circumvent the physics models entirely. Now that's an approach people sort of take in different disciplines, especially in hydrology, to a limited extent, but then these models that are empirical in nature ignore the physics, so they can come up with solutions that are completely inconsistent with physics. And then how do you put them together is actually something that sort of is going to be talked about here. But this paradigm itself was motivated by our feeling that these machine learning algorithms have to be more and more aware of the physical information, and that's what I'm going to talk about next in the context of land cover change detection, and mostly, and nearly all of it using data from the satellites. And I'm going to talk about 3 different problems, but let me first give you a very brief overview of what the data looks like. Okay? So the satellites sort of went up into the sky for more than 40 years ago, started collecting data, and a number of them are sort of now available. The number of data sets are available in public domain. And there are many of these data sets are available also from companies, for profit companies as well. So let me give you an example of one data set that's available about the Earth starting in about February 2000. This is data from the MODIS sensor launched by NASA. I guess NASA developed this sensor. It's on 2 different satellites, Terra and Aqua. On every single day, the sensor is taking a picture of the Earth at every single place. You look at the campus, the Fort Collins campus, you look at the sky, you're being pictured every day, at least once. Okay? And the picture is very coarse. If it's a square kilometer pixel, it will take about 16 pixels at most, depending on different bands. Okay? So the pixel could be 250 meter by 250 meter wide, or 500 meter by 500 meter wide. Right? So very coarse pixel. But because you have this data every single day being captured and stored all the way from 2000, you have a lot of information. Right? You can take this information and collect it and create mosaics like these for every single time and space. So if you look at a single date, your data may look like this. You take the multispectral data, you convert it into some sort of a index, like the greenness index, and the data would look like this. That is, you can sort of see one day's image of the Earth converted into this greenness index can already give you quite a bit of information about the Earth. You sort of know where the rainforest, tropical forests are, right here. All of the great deserts are in the world, right? You can also tell that this picture must have been taken in summer, okay? Because Midwest, Minnesota, where I live, is green. If you take this picture in January, it's going to be all white. It will not be distinguished from any desert area, right? So any single day, you can see so much just by looking at it, right? Now, at any location, you can see how the greenness is changing. So here is a location, and I'm showing you for a single pixel, the location's greenness starting in 2000, and it sort of goes up and then comes down, and then goes up and then comes down, and so forth, right? And then around here, something changed, and it became something different. So you can look at the variability of any information, in this particular case, greenness, right, at any single location. So you can have so much information about the entire globe in space or at a single location in time. And if you look at this, this location happens to be the greenness at the location I was giving a talk at in the China National Convention Center. So I took their pixel, and this is how it shows. And can you guess as to why this has this kind of a pattern? They built a convention center, and why they built a convention center? Actually, they built the convention center sits at a place where the Olympics were held. Okay? So Olympics were held outside Beijing, and this was it was a farmland. It was a cheap area, right? So, and once, of course, they converted it, they built the convention center, it was all concrete, very low vegetation, and now if you go there, there are fancy multi-million-dollar apartments. So they have the grasslands and everything. So you can see that here, right? So the point is that yes, any location on the earth, something is happening. You can find out just looking at even some single variable, but of course, as a computer scientist, we have much more information available to us. This is very coarse data. We have Landsat data going back 40 years, but at a much finer resolution, but much less frequently. Europeans launched a satellite a few years ago, much better quality data, but high resolution. And then there are corporations that have launched these satellites where you can have a daily image of the Earth if you pay for it. Okay? At about a 3-meter resolution, you can find presence of cars in the parking lot and things like that. Many things on a daily scale. So I'm going to show you what we did using this data and machine learning. And this talk is at a very high level. I was told that this audience is very broad, so I have to keep it very generic. So I'm going to talk to you about 3 different applications. Being able to map tropical forest fires on a global scale. Okay? This relates to conversion of tropical forests into agriculture, like plantations. And this is, I may mention, there's a huge interest in the ecological community about how the water on the surface is changing. And then, of course, this is an extremely important problem from the perspective that some of the biggest impacts of climate change would be felt through water, one way or the other. So let's come back. Why are we interested in mapping fires in the forest on a global scale? Forests, just by their natural growth, catch as much carbon from the air as almost the entire transportation sector. All the planes, trains, cars, ships put together, they're catching as much of the carbon just by simply growing. So they're very important. They play a very important role. But the bad news is that if you look at the amount of carbon that is lost from these trees because of fires and degradations and such, it's of the same order. Okay? So we are losing money on the table. We want to be able to go to zero carbon economy one way or the other, and forests could be playing if we keep the forests healthy and let them grow, they could give us a free ticket to drive our cars even using fossil fuels, right? Now, given the importance of this problem, there's a lot of work in this area. The methods work extremely well in parts of the world that are not too close to the equator. And it turns out that most of the tropical forests happen to be near the equator. The data is very cloudy and very difficult to observe from the satellite. And so the question is, can we build a methodology that can find these fires, identify them, monitor them, going backwards in those areas? And so we have to build an entirely different methodology to be able to find, identify these forest fires when we don't have the presence of a ground truth because of the clouds and other issues. The other big problem related again to the degradation of forests is that as the population has increased over a period of last 50 or so years, you know, about 100 years ago the population was about 1 billion, now we are 7 billion and increasing constantly. So the food requirements have gone up and people are converting more and more of the tropical forest into these plantations for sugarcane, for soybean, in this case for oil palm in Asia, which you're seeing here. And there's a big push on a global scale to make sure that we don't source any product that are coming from the tropical deforestation of tropical areas. So if you open your kitchen pantry, almost every product that you have in the pantry has some palm oil. Okay? And that palm oil comes from these areas. And some of the biggest corporations in the world have promised not to source their product from these deforested lands, but there is no way of knowing whether the oil palm plantation that you're looking at, was it deforested or was it just an agricultural land, you know, for a long time? So being able to figure out how this plantation dynamics is evolving is an extremely important problem. Has been very little information about this so far, and then we can show you machine learning, what machine learning can do. And I mentioned to you about the dynamics on the water. That is, again, it required novel methodologies to be able to find these things. So for each of these three problems, I'll give you very, very brief introductions, a little deeper ones, show you results. You can certainly read our papers to learn more about it if there's interest in a very specific topic. But rather than going to the technical details, I like to make sure that you have a sense of, yes, machine learning could do something in each of these areas. So don't mind me flipping through many of the slides. I've given longer and shorter versions of this talk. So if my slides are all on the web, so you can certainly take a look at any of them. So the very first talk, the very first problem involves, by looking at the multispectral data from the satellite, which is available, you know, going back, you know, from different sensors, how do you identify if a certain pixel, certain location was burned or not? That's the idea. And again, you're doing it only for the forested area. And it would seem to someone in machine learning a fairly simple problem. That is, you give me the training data, or give me the label data, give me examples of pixels that are burned, examples of pixels that are not burned. I look at the spectral values, I create a training data set, and let's say 1 means burned, 0 means not burned, and I have the spectral values, X is the vector. Once I have that, I can just throw that into any machine learning model, including the most recent deep learning models, and I should be able to build a good model. And finding these data sets should not be too hard, because you can always look at a satellite image like this, for example, and if you watch the satellite image over a period of different days, in this location, you will know that it looks green most of the time. When the fire started, it became brown, and then eventually it became green again after the trees grew back. So you can sort of be certain this was a fire, and then it's not a fire. So you can get it. So this is sort of how you would get started. Now the problem is that if I'm trying to solve this problem for a tropical belt on the Earth, I have to assume that I don't have these labels. The reason I don't have these labels is that when these fires happen in the tropical areas, the fires can burn for weeks and months, which means you don't have the satellite data available to you. You know, most of the time you'll see that just a cloud. Okay? Or you will get very, very poor images that will be very hard to interpret. Right? So which sort of forced us so as a result, you have very, very good labels in the North America. I mean, in California, you see a lot of fires. And at the end of each year, California state basically would issue polygons, maps of the fire. That is, these are the areas that burn. Okay? And they're very, very accurate maps. So California has a very, very good labels. The rest of the US has not so good. Canadians do a very good job. But the rest of the world is actually pretty poor. So you have to assume there are no labels there. And if you build a model in California or North America, and if you try to apply it elsewhere, it can get very, very bad results. So even a model from California doesn't do as well in Georgia as opposed to, you know, but in the models that people have built, very sophisticated models, they tend to miss most of the fires, a very large number of fires in the tropical belt. So that's one big problem. Second problem is that the model that we're building, the target value that we're trying to assess, is relatively rare. So California has about 70,000 square kilometer of forested area, one very large area in California, right? And if a couple of thousand square kilometer burns, it's a very, very large bad fire year. 2008 was a very bad fire year. The current year is a very bad fire year. And these years, we have sort of burnt about this much of the forested area. But this is still a small fraction of the total forest. Now, these machine learning frameworks actually are oftentimes are designed for cases when your target class is balanced. And if it is imbalanced, then a simple model which simply calls everything to be unburned would have a very good accuracy. So even a small false positive rate can be really bad for you. Okay? So which is why you need to sort of build models that are cognizant of this deep ratio of the positive negative class. And then of course the third thing is if I don't have labels and if I'm trying to build a model that works in tropics, how do I know that my model is really working well? How do I build a model without really having a good view of any aspect of reality? So all of these challenges are actually very, very big, and it requires development of a new paradigm. And I'm just going to give you a very brief introduction to something we did to address this, but then the overall results I'm going to show you would, of course, have all of these three things built into it. And what we are sort of talking about in the very first case is that I'm trying to build a predictive model. I don't have the right labels. Can I still build a good predictive model? Right? And to what extent can I do it? Okay? So if you keep that picture in mind, what I'm sort of trying to represent here. So basically, what I'm talking about is that I have, this is a standard machine learning framework. That is, I have rows of examples, training sets, the training samples that I have. The columns are variables, which are the features, and the last column is the target variable that I'm trying to predict. In this case, did the forest burn or not? Did the pixel burn or not? If I had this training data and it was representative, I will be able to take any out-of-the-box machine learning algorithm and apply it, and it should do a pretty good job, except for the second and third challenges that but I don't have this, okay? But I have to have something to be able to build a model, and what I'm going to assume in this particular case, instead of having good labels, I have labels that are really, really bad. Okay? Now, you sort of say, well, how do I find bad labels? And it turns out that in many cases, it is possible to find surrogate labels. Okay? So for example, for the burned area, the real thing you only want to know is for each pixel, did it burn or did it not burn? Okay? You don't have that, but the ecological community, of course, cannot wait for this thing to be solved. So they use oftentimes thing called thermal anomaly. So the satellite is also capturing whether a certain pixel appears to be abnormally warm, abnormally hot compared to the normal. And if it is there, let's call it a signal. And it turns out that this signal of thermal anomaly is not very good. It will miss a lot of fires because maybe the fire was burning and the satellite was not on top of the pixel at that time. It could catch a lot of superfluous fires or very partial fires. Because even a small fire in a neighboring farmland could make the pixel anomalous. So we have labels that are not quite perfect, and we're going to capture the imperfection of these labels compared to these good ones by this probability that this blue, which is let's say positive, get replaced by a red with the probability of alpha, and this red, which is negative, gets replaced by a blue with the probability of beta. And of course, if alpha and beta were very, very high, let's say they were both 0.5, then you would say my labels are complete garbage, which means nothing you could do with this. If I give you complete garbage, then there's nothing you can do. So this sort of gives you the ideal case scenario. This is the scenario we're looking at, and the question is where are we going to get imperfect labels? For the burnt area, we have thermal anomaly. For urban settlement on a global scale, we use the nighttime light. And if I am trying to sort of apply this to something like a recommendation system, let's say for an e-commerce company, I don't know exactly whether this person has bought anything, has shown any interest in a certain product, but I may know of the interest of its friend circle, and that could serve as a potential imperfect label. Right? So this is sort of the setting. The question is, in this setting, can we build a complete machine learning framework that would solve the problem? And again, this might be almost the extent of my technical details. That is, when people build the supervised models, if you have these expert annotated labels that you can trust, and if you have them plentiful, it's a textbook problem. There's nothing really much to do. If you don't have enough samples, but whatever you have are really good, there are a whole series of methods people have developed in our community. But we have neither this nor this. We have only imperfect labels. Now, if you have imperfect labels for many, many different annotators, then people have developed very sophisticated techniques to be able to use them. So people use this thing called mechanical Turks to be able to label certain things. These are all individuals sitting anywhere in the world for very little money. They're labeling, they're doing some jobs for you. None of them are perfect, right? But they will be making mistakes, but the mistakes are not likely to be in coordination because they're sitting far away. And using that concept, people have developed a whole series of works that can work with multiple annotations. We don't have the luxury, we only have one annotation. Now, within one annotation, then there has been quite a bit of work in the direction of partial supervision. That is, you have two labels, positive and negative. You have a few examples of positive that are really good, but the rest you don't have anything. It's called partial supervision. That scenario occurs in many, many situations, and people have developed a series of works in this direction. But I don't have partial supervision. I have both bad labels, both for positive and for negative. Right? So I have imperfect supervision in the worst case sense. And even here, people have developed methods in which both the positive and negative classes are balanced. In which case, people have built methodologies in the last few years in which they can handle this problem. But we don't have this either. We have one of the class is highly balanced. So these methods don't work. So a methodology was built which actually sort of piggybacked on the advances here and here and here to be able to sort of build a complete framework, which I'm not going to be able to talk about because of short of time. It'll take much longer. And that methodology basically was able to we call it wrapped rare class prediction in absence of ground truth. It has 3 different steps. The step number 1 is making sure that if I give you this imperfect labels with certain requirement, your predictive model will be almost as good as the one that you would build using perfect labels. So this is the first step. But then this model, no matter how good it is, will have certain false positive rate. And if you have imperfect, imbalanced distributions, your error rate would become very high. So the step 2 sort of takes care of that aspect. And then the step 3 sort of refines the results further. So this is the extent of my depth of information I'm going to give you here. But I just want to show you some results. And first I'm going to show you results in the context of a scenario where we know everything, which is California, where people have perfect data. So in California, we have ground truth, which means given that product that you get from California State, I know exactly how many fires were there, and every one of the fires I know is correct, right? In the sense that it's a perfect result. So this is the ground truth label. And if I build a classifier using this ground truth label, my classifier isn't perfect. It gives me about 82% of the fires, and of the location that it calls fires, only about 30% are correct. And this is, of course, because the models are trying to build this model, predictive model, machine learning model, is using the perfect label data, but it can only do as good as information exists in the feature space. Now, instead of, so this is the best you could do with this model because there's a very high false positive, right? But instead, if I had a weak label, which is the thermal anomaly, by itself is not very good. It finds about 80%, 88% of the fires in California. And of the fires that it finds, about 42% are correct, the rest are wrong. So this by itself is not good. But if I use this as the input to my predictive model, my predictive model actually is almost as good as the red one. So this one uses perfect label, which I don't have. This one uses imperfect label, which I do have. And it's almost as good. But this is step 1. Okay? Step 2 shoots up the precision at a loss of recall. And the step 3, and the step 3 gives me a very, very high precision and almost as much recall as the best model I could give. Similarly, if I sort of look at the labels from Georgia State, you can see the performance increasing like this, Montana State, and so forth. But these are all the places in the US where we know what's going on, and really that's not of interest. What the real interest is in places like tropical forest, this tropical belt. And in this belt where a lot of the deforestation is happening, it turns out that the NASA state-of-the-art product sort of says about 180,000 square kilometers got burned and burned over the last 2 decades. And it turns out that even a very conservative version of our machinery finds about 3 times as much area that was burned, right? And to give you a physical sense of what that looks like, to sort of see as to does it really mean much, you can sort of see that if you look at a tropical forest in Brazil, this is a picture from a Google Earth image from 2002. It looks very dark green here. This is how rainforest looks like. It is except these white areas, which are roads and some deforestation here. Same picture from Google Earth in 2015, and you can see all of these white areas here. They're all deforested areas, right? The picture that you're seeing here is just the pixels that were identified by the algorithm as being burnt, right? Now, if you look at these two, all of these burned locations are exactly following the same parameter. This one is simply looking at the burned information. Look at this feature, this feature. You can see this thing here. You can find anything here. This line here, you find this line here. So every feature you see here, you can see here. Now the yellow and red colors, the difference is red and yellow are found by our algorithm, and red points are found by only by the NASA's algorithm. So basically, yellow points are the ones that are found only by our algorithm, and you can see the impact of what this thing does. So this sort of tells you how a systematic machine learning framework can sort of build these kind of products. And this is just sort of one application of this methodology. We have sort of used the same thing to build the urbanization maps. And rather than spending time on the second thing, what I'm able to show you is similar methodology was built to see the dynamics of plantations in the tropical world, which again has been extremely hard for people to be able to do. So you look at the red area, these are the plantations, oil palm plantation as of 2000. And all of the green areas are the ones that are sort of becoming plantations year after year after that. Again, was found using a paradigm that we built using. So you can basically study for any of these areas exactly what the annual changes are in the area. So for each pixel whether this was deforested and when it was deforested, right? And to give you another sense that these areas, and when people try to deforest them, they have to get a license from the government. That I'm going to build a plantation of about 10,000 acres, and then you get the permission to build a plantation there. And they're supposed to cut the trees, move them away, and then put the oil palm plantations there. But much easier thing for people to do is simply burn them. It's much cheaper, much quicker, right? So let's see how. So we know using this machinery that here are all the locations, green locations that have been converted from forest to plantation in the 18-year period since 2000. Some of them were converted properly, and some of them have been burned and converted, right? So let's see. So what I'm going to do on the next slide is convert some of the green pixels into red pixels. And red pixels are the burned ones. Right? So you can see quite a few of them are burned. Right? Now imagine somebody over here tried to put a plantation. And they of course burned this, right? And the plantation of course is only this much. But if you're trying to burn some trees, do you think the fire respects the boundary? That you want only 10,000 squares, and I should really want only 10,000, but what's the point of burning the rest, right? So do you know how much collateral damage happened? I'm going to show you next with the blue color. So somebody in the process of burning this fire ran amok. So this sort of tells you as to why this could be very important, because then you can punish people. Saying, hey, look, not only you burned, you did the wrong thing, but look, this is how much damage you caused, and so forth. So there's a teeth you can put to the monitoring. And again, all right. So now, in just a few minutes I have, I want to cover this last topic of being able to monitor the surface dynamics. I'll skip the motivation, and just remind people again, when I give this talk to people in machine learning, that for this particular example, we do not have a shortage of labeled data. Okay? Why? Because on February 2000, NASA flew a special mission of the space shuttle just to map water on the Earth. Right? So the shuttle just went around and shot radar beams just to sort of see where the water bodies may be. Okay? So we have a pretty reasonable picture of how the water on the surface of the Earth looked like on February 2000. Okay? But of course, because of the human actions and changing climate, these water bodies have been shrinking and growing, and you will see in a few minutes as to where they're happening. So you want to know the dynamics. You want to sort of know if you put up a dam, is it shrinking? If you have water bodies appearing in places you didn't expect, are they disappearing in places? So one point would be that while I have a lot of data from February 2000, a whole bunch of communities have already built using the data, the fixed maps of lakes and water bodies, all going back to 2000. So you can have a lot of training data for those, but then can you build a model that would work everywhere, and then you can apply it elsewhere? And the trouble is that because of the heterogeneity in space and time, the data that looks on one day looks very different on another day. The data looks at one place looks very different in another place. So this is a rendition of the multispectral data in red, green, blue space for 3 different lakes in Africa, northern Africa. And you can sort of tell that middle bodies in each one of them is water, and yet the color of water looks different in each one of them, and the color of land surrounding them looks different in each one of them. Same lake on 2 different dates could look very, very different. So there's a lot of heterogeneity, which means the straightforward approach will not work. But that's only part of the story. Much bigger story is lots of time data is simply not available. So whenever you look at this pink color, which is most of the time, data is missing. Okay? And when the data is missing, we have no labels. Okay? But much worse, data you may think the data is available, but actually it could be bad data. And then you have labels, but they're really garbage. So because of all of this, the quality, any machine learning algorithm could actually fail miserably at times when you really need it. So it requires development of many different approaches. And this is, of course, building better classifiers that can handle the heterogeneity. But the piece that sort of forced us to think about quote unquote physics and bring it into machine learning, which actually eventually turned the inspiration of bringing physics into the models later on that we're working on. It's sort of coming over here, and it's very, very simple. That is, water bodies are being labeled by machine learning algorithm at each pixel independently. But really, these bodies are physical bodies in a 3-dimensional space. And a water body would be forming in some sort of a bowl that you're seeing on the Earth. Let's say there's a bowl here, this cross-section of a bowl, and which means that labels that you're going to give on this bowl cannot be arbitrary. Right? For example, either this bowl is filled up to water up to here, or up to here, or up to here. It cannot be that this pixel is water and this is land. That's clearly wrong, right? So using this intuition, you could actually take output of any algorithm from classification and improve it, right? Except that this elevation information is not available, or often not available at the right resolution, or even if they're available, for example, some very high resolution elevation mapping satellites are being launched, this elevation could be changing over a period of time, and you can already capture that. So we built a machine learning machinery which actually keeps this concept in mind and then improves the labels automatically to be able to be consistent with them. And using this, a whole system was built, and I'm going to show you 2 different versions of this. This is the one that, of course, anybody can go to this link and see the water bodies on the Earth, several thousands of, almost 10,000 of them, that are being picked up by the MODIS sensor, which is each pixel is about half a kilometer by half a kilometer. Every water body that has at least 10 pixels, which means total area is about 2.5 square kilometer, would be there. And then you can look at these water bodies, you can see how these bodies are changing, you can see which one of these bodies may be increasing or decreasing, you can see phenomena like melting of glaciers, changing rivers, structures, and so forth. So I'm going to show you a few examples just to give you so if you look at this area, you see a bunch of dots, each of them is a water body. One of the dots corresponds to a dam called Don Martin Dam in Mexico. The system, when you're up there, it will be, in addition to sort of showing you the picture, it'll show you the time series, like how big or small the water body is on different dates. So on some dates, the water body was as big as 800 pixels, which is about 200 square kilometers, pretty large water body. But on some days it has shrunk quite a bit, and it has been sort of having this kind of dynamic. So you can sort of see how this water body may be changing in size. You can also see the annual Google time-lapse images that are available for many of these water bodies. The system allows you to sort of check these, and if you watch these carefully, you will see it increasing, decreasing exactly in the same format. You can also color these water bodies in terms of whether they're increasing or decreasing. So on this map, all of the increasing water bodies have been colored red, all of the decreasing water bodies have been colored green, and you can start seeing a whole bunch of patterns on a global scale. And I'm showing you only South America here. Oops. So for example, you see a very large area here of green dots. If you zoom in over here, you see almost everything is green here. If you count the total number of pixels in this area, it was about 10,000 pixels at one time. It's about 2,000 square kilometer of water, and it shrunk down to something almost nothing. This is an agricultural area, a lot of farmland, and somehow they might have overused the water or something. There's a big difference here. You can actually see every one of these water bodies, basically, the dynamics of it from Google time lapse, and you can see it's sort of growing and shrinking at the same rate. You can see a whole bunch of red dots in the Tibet. Right now, this means the water bodies are increasing there. Right? This is not a good news, okay? Because people have been suspecting for a long time that as the temperature is increasing, the glaciers are melting. And when the glaciers melt, of course, a lot of the water runs off into the rivers, but a lot of them get trapped into these lakes. So people have been sort of trying to build these maps. Like for 1990, for certain areas, people say, oh, this is how the water body looks like. Or for 2000, for certain areas, this is how the water body looks like. Now, we have a dynamic map of every single pixel every day, for the entire area. And you can sort of actually see that. Here, if you zoom in here, the system would let you sort of see that these are the original water bodies, and this is how much they increase in 18 years, right? You can see again the increase of this area. So this is the increased area. So that slivers of the increase. You can actually see them. You see the water body here. This is increase, and you can see that increase here, and you can sort of see this is how it grew, right? So you can sort of see that each one of these little areas are actually increasing water bodies, and you can actually count how many pixels of water emerged. Almost 40,000 new pixels of water emerged, which is about 10,000 square kilometer of water shows up in the Himalayas. Very massive amount, pretty serious stuff. And you can study this. You can figure out exactly how is the change accelerating? Is it decreasing, increasing? What's happening? You can see the courses of rivers on the global scale. The rivers meander oftentimes because of sedimentation, right? So there's a lot of deforestation that goes on in the Amazon. So the sedimentation would go into the rivers, and then they will start meandering. And you can see the meandering process all over the globe. Analyze it on the fly of your fingertip. You can see islands shrinking. You can see this little area identified by the algorithm saying this is shrunk. And you look at the Google time lapse, you will sort of see this shrinking pretty much the same way. You can find dams being constructed because dams sort of show up as water bodies that were not there before. It's very easy. Once you find the time series of the water bodies, it's very easy for a computer science student to sort of write down an algorithm that will find these jumps. You can find all of these dams. Now, dams are something people study a lot. There is a database called GRAND maintained by the hydrological community, which maintains all of the dams that they know about. This database was very current until about 1998, 99, and since then they have been relying on people reporting, self-reporting. This is how many dams this database has to be built since 2000. This is how many our algorithm was able to find. And each one of them, of course, you can see the concrete, so you know they're real dams. So this was all the results being built at 500 meter resolution. That means a water body has to be at least 2.5 square kilometer large to be able to be in the system. Now we are actually building converting this very coarse information into a fine-grained information using a series of, again, machine learning technologies. And this one can go down to as much as 1/10 of a square kilometer water body. So we have about 500,000 water bodies in this database. It's being constructed. I'm finishing in 2 minutes. So you can sort of see, and this, of course, there are 500,000 water bodies. This program is processing them one by one. So this map shows you about 1/3 of these being done. Another couple of months, we'll have the entire surface mapped at a very fine resolution. And this is sort of the kind of thing that's sort of going on. You have the data that is being produced at a very coarse level. You can see this at 500 meters. This is how the boundaries would look like. But the reality underneath is much finer. This is what you would like to be able to see. So this conversion of very coarse data into a very fine data is being done, again, using combination of algorithms in machine learning that sort of uses physical interpretation. And I sort of tell people in computer science that this is almost like taking an image of someone which is very, very coarse and converting into something very, very fine. Now, this is something our machine learning algorithms can do today. And how do they do it? They will take millions of images of people. They will have both the coarse version of them and the fine version of them. They will learn the mapping, and then you will give them a different image, and they will be able to construct a fine thing just like this. With a lot of data, they can figure out if there's eye here and there's eye here. The nose cannot be arbitrary, so it has to be sitting in some place, and so forth, right? But here, I could do the same thing if I had lots of views of the same lake on different days, and I could convert this into this. I don't have that. So being able to do this process over here without having data involves physics plus machine learning. So this is sort of what you're seeing is in action, right? So again, so these are sort of some examples of bringing physics and machine learning. I just like to conclude by saying that there's a huge opportunity of sort of for our field in computer science to be able to compute to the environmental sciences, but also it also is an opportunity for us in computer science to advance our field by working on these problems. And these methods have very, very wide applications. And one of the big driving factor of this direction is being able to use the theory or the physical knowledge or the scientific knowledge in advancing these data science algorithms. All right, I think with that I'm going to stop. I guess I've used up a lot of my time, but I'll take any questions. Thank you.
Thank you. We have very little time for questions, but I will just announce one more time that there will be another talk at 2 p.m. right here again that goes into more of the details of how to use physics. Do you want to say in 30 seconds what's in the second talk?
It's like the objective of the talk is to be able to take basically the dichotomy of physical models that run their dynamical system models that are sort of simulating a phenomena and addressing their limitation by combining them with machine learning approaches to make them better, but without ignoring the inherent physics inside them, but rather augmenting it with machine learning approaches. So this is sort of the 1-minute summary of it.
Do you have time for one or two questions? Okay, one question. Who wants to ask the one question? And by the way, anybody who wants to, especially students, can join us for lunch. Peter Jan, do you have a question?
There's a question here at the yeah.
Only a question. Okay, thank you very much for your very nice talk. So the question is about, let's rate my ignorance, I guess. So what you do the classification.
So you do the classification. Do you also attach an uncertainty estimate to that classification?
So there are the uncertainty comes in many different aspects. The very first one about mapping the forest fires. The third item was about uncertainty classification. How certain am I that this is really a good result? So we can put some bounds on it, right? And similarly for the water body, we can provide bounds as to whether the labels are really confident versus they're not so confident. And again, based upon the physical notion of the bowl shape.
Well, before we end, we just want to present to our distinguished lecturer just a token of our appreciation. Let me read just from this presenter to Vipin Kumar in appreciation for your Information Science and Technology Center ISTEC Distinguished Lecture.
Thank you very much.
Thank you all.